Hello everybody. So today's talk is privacy enhancing technologies for mobile application, and the speaker is Dr. Urs Hengartner. He's a professor at the University of Waterloo, David Cheriton School of Computing Science. Urs, thank you.
Good afternoon. Thank you for having me. I'm a member of the CRISP lab at the University of Waterloo. This is the cryptography, security, and privacy lab, and I'm going to talk about privacy-enhancing technologies for mobile applications. This slide it shouldn't be new to anyone here. On today's cell phones, most of them now have some sort of positioning capabilities, which allows them to figure out their current location using GPS, using nearby cell phone towers, whatever. And using these positioning technologies, it has become possible to introduce several location-based services and applications. Two examples are listed on this slide. I'll take a more closer look at them later in this talk. So you can imagine having a social networking application, similar to Facebook, MySpace, whatever, that takes users' location or users' proximity into account. Or you can also imagine a service that returns nearby points of interest to people. For example, this is what you can do when you use Google Maps. Now, there's a problem with all these location-based services and applications. In particular, the problem is about location privacy. So if you know somebody's location, you might be able to derive sensitive information, sensitive personal information about this person, information about her activities, her interests, her political preferences, her health, right? If somebody's at the gym, for example, she's probably doing sports. If she's at a soccer stadium, she's interested in soccer. If she's at the headquarters of the Liberal Party, she might be a member of the Liberal Party. If she's at the mental hospital, she might be sick, but maybe she's also just visiting somebody, right? And so therefore, we have to be very, very careful when it comes to revealing our location to other entities while using a location-based service or location-based application. In particular, what we need are privacy-enhancing technologies. So technologies that allow us to use these location-based services or applications without having to give up our location privacy. For example, without having to reveal our precise location to a service or to a friend. And I will look at two specific kinds of privacy-enhancing technologies in this talk. So let's start with the first example. This is the web page of a company called Loopt. You might have seen it yourself. I don't think it's available in Canada, but it's available in the US, and so it's supported by many of the big US cell phone companies. Some of them are listed on this slide. And so some of the features are also given. In particular, so you can do things like if you go to a restaurant, you can write a review and then post it to Loopt, and when somebody else is close later on and is thinking about going to the restaurant, he or she can look at the review. And there are other activities that are very similar to the activities in existing social networks. You can share your photos, your location, and comments. Now, the feature that I'm most interested in is the first one, and I highlighted it on the right side of the slide. In particular, what this feature allows you to do is it allows you to connect with friends, and it alerts you whenever a friend of you happens to be nearby. Now, if you think about this feature in more detail, in order to be able to implement this feature, Loop has to know continuously all the time your location and also your friend's location. And obviously, from a privacy point of view, this is troublesome. So the question arises, can we do better? Can we build a distributed version of Loop, so a version of Loop that does not require this trusted third party that always knows where we are, where I am, where my friends are? And so what I'm going to do for the next few minutes, I'm going to outline some possible solutions and outline how they're insufficient till we will converge on a final solution. So the first solution is very straightforward, right? Today's cell phones, well, they're smartphones, right? They can do all kinds of stuff. And so let's just do the following. So Alice and Bob, they are friends. So Alice's smartphone every 5 minutes or so, it determines its location and sends its location to Bob's smartphone. And Bob looks at the received location and checks whether the two locations are close, and if so, it is going to raise an alert. Well, now we no longer have a third party that can track everybody, but in this solution, it's still possible for Alice and Bob to track each other. So that's not what we want either, right? Alice and Bob, they should learn of each other's location only if they are nearby. So let's try again. So what Alice could do is, Alice could encrypt her location before sending it to Bob. Now, obviously, for this to be useful, Bob should not be in the possession of the decryption key, because otherwise he can still learn the location, right? Now, the problem now is, in a traditional encryption scheme, this doesn't really help us much, because, right, a ciphertext, there's not much you can do with the ciphertext. All you can do is you can decrypt it, but Bob doesn't have the decryption key, so Bob gets a ciphertext, but there's nothing he can do with it. Now, there's an interesting observation in that there are modern encryption schemes developed in the last 5-10 years or so that allows to do operations directly on a ciphertext. And this is what we're going to exploit in our application. So one of these schemes is called homomorphic encryption. So what is this? It's a public key encryption scheme. I assume most of you have heard of public key encryption. So there's a key pair, there's a public key and a private key. Anyone can use the public key to encrypt some information, but you need a private key in order to decrypt this information. And so in the rest of the talk, I'm going to use the notation that EA of M is the encryption of a message M with a public key A. And so the interesting feature of homomorphic encryption is the following. If we have the ciphertext of two messages, and this is all we have, right? So we have only the ciphertext of two messages, then we can compute a ciphertext for the sum of these messages, right? So on the slide, we have EA of M1 and EA of M2. That's all we have. So we take these two ciphertexts, we do some fancy processing on them, and what we end up with is an encryption of the sum of M1 and M2, right? And we don't need to know M1 and M2. It doesn't matter how exactly this works behind the scenes. If you're interested, I can give you the details after the talk. By the way, please feel free to interrupt me if you have any questions. What would be really cool is if you could also if you could also compute the product of two messages in this way. Unfortunately, we are not there yet. Despite this the lack of this feature, we can still do quite an amazing number of things using homomorphic encryption. In particular, what you can do is the following. Alice uses homomorphic encryption to encrypt her location and sends it to Bob. Bob then encrypts his location using, again, homomorphic encryption and uses the received location from Alice, which is a ciphertext, and the ciphertext for his own location that he just generated, and combines them using this homomorphic encryption property and computes the distance without actually learning the distance, right? This is the cool thing. So Bob doesn't learn any information, but he's still able to compute the distance between Alice and Bob. And so he simply, after having computed this encrypted distance, he returns it to Alice, which is going to decrypt it, and then she learns the distance. So here Bob doesn't learn any information, but we still have a problem. Alice, she can always learn the distance to Bob, and that's not what we want. She should learn the distance only if Bob happens to be nearby, so if the distance is small. Now, as it turns out, there are a few additional tricks with the help of which we can implement this feature. So Alice will be able to decrypt only if the distance is small. And on the next few slides, I'm going to outline two possible tricks to do this. Before I do that, let's take a closer look at the actual protocol, how it works behind the scenes. So Alice and Bob, what they do is they jointly compute the distance. So this is the second line on this slide. And so, right, this is just a standard distance computation. Well, actually, what we compute is the square of the distance. It doesn't really matter whether we need the square or the distance, and both of them are sufficient for our purposes. In particular, computing the square is cheaper. So we compute the distance first, and then we subtract the square of a value r. And r is the distance that Alice and Bob consider nearby. Right. So basically, if d is equal or smaller than 0, Alice and Bob are considered nearby. And so what our protocol does is it computes this value of d without Alice and Bob be able to learn the actual value. And so what we're doing is, right, the third line on the slide shows the formula for the distance commutation, just in a slightly different form. So Alice and Bob, they now compute each of the terms in these formulas, right? So for example, Alice computes the encryption of XA square and all the other values that depend on her location, and then she sends all the ciphertext to Bob. Bob computes, for example, the encryption of XB square, and he also computes on, for example, 2XA to get the encryption of 2XA XB. Again, Bob is not able to learn Alice's location. And finally, Bob ends up with the encryption of the distance. But now Bob can't simply send this value to Alice, right? Because Alice then could simply decrypt this ciphertext, but she should be able to learn the value of d only if the two happen to be nearby. So what can we do instead? Instead of having Bob compute the encryption of d, we have him compute the encryption of d plus a random value v that is chosen by Bob. And so Bob returns the ciphertext of d plus v to Alice. Alice can decrypt this value, but it's going to be completely useless to her, right? Because it's d plus v. We randomize this value. It's no longer the actual distance. So Alice cannot learn any information from the decrypted information, any useful information from the decrypted message. Instead, what she's going to do is she takes this decrypted value and gives it to a third party, Trent. This could be a joint friend of Alice and Bob. And similarly, Bob gives v, so the random value that he chose, to Trent. And so now Trent takes these two values and computes d, and then informs Alice whether the two of them are nearby, right? So Bob learns whether Alice and Bob are nearby, and this is the only information. Trent learns whether Alice and Bob are nearby, and this is the only information that Trent learns, and he notifies Alice and Bob whether they are nearby. Any questions about the protocol so far? So this works. The problem is we have this, what we call this semi-trusted third-party Trent. We have to rely on Trent to behave properly, right? Not to cheat, not to be malicious, not to tell Alice that Bob is not nearby, even though Bob is found to be nearby. Also, in this protocol, while Trent cannot learn Alice and Bob's location, he can still learn whether they are nearby. And right, maybe this could reveal sensitive information, like if maybe all of a sudden, if Alice and Bob happen to be nearby a lot, maybe they are more than just friends, right? So this can be sensitive. And also, Alice and Bob, they have to trust Trent not to collude with the other party. Because if Trent colluded with the other party, for example with Bob and Trent, they could always figure out the distance to Alice. So ideally, we wouldn't need Trent. And so that's what I'm going to do next is I'm going to outline a solution where we don't need Trent. So Alice and Bob are the only two parties that are the only two participants of the protocol. Again, we use homomorphic encryption, but this time we use what I call homomorphic encryption with a twist. In particular, there is a homomorphic encryption scheme where the owner of the decryption key cannot actually decrypt the ciphertext. Right? The first side, this might sound weird, right? Why do we have an encryption scheme where you can't actually decrypt a ciphertext? Well, if we couldn't do anything with the ciphertext, then indeed the encryption scheme would probably be completely useless. However, what we can do in this scheme is the owner can check whether the ciphertext is an encryption of a particular plain text. For example, if the owner thinks the encrypted value is the value 0, the owner can take the value 0 and check whether the ciphertext is an encryption of the value 0. What this means is if there are lots and lots of possible plain texts that can become encrypted, and the entity that generated the ciphertext randomly chose one of these values and encrypted it, it is very, very unlikely for the owner of the decryption key to figure out the value that was encrypted. Right? The only thing the owner of the decryption can do is take each possible plain text and check whether this plain text was encrypted in a ciphertext. But if there are lots and lots of possible plain texts, it takes way too long to do this. So therefore, this scheme works only, the owner can learn a plain text only if he has a good idea of what the encrypted value could be. Excuse me. So this is the first part of the piece that we need. The second piece is we need location grid. So we change the scenario slightly. Instead of inputting actual location, like location at the granularity of meters into our algorithm, we compute or we use a grid. Right? So our position is now the cell in a grid. So you can think of the grid as being consisting of cells that have a width of about 100 meters. Right? So basically the way the scheme works is we take the accurate location, like in meters, and divide it by r, which is about 100 meters, and get a grid cell. And then we compute the grid cell distance. Right? So Alice and Bob each have a cell, and we compute the distance between Alice's and Bob's cells. And so if Alice happened to be in the same cell as shown on this slide, then the distance is going to be 0. If they happen to be in two adjoint cells, the distance is going to be 1. And if they happen to be in two diagonally adjoint cells, the distance is going to be 2. On the other hand, if Bob is farther away, this distance is going to be larger than 2, as in the example on the slide where the distance is 5. Right, and so now we consider Alice and Bob to be nearby if D is either 0, 1, or 2. And so now let's take the two pieces and combine them. So Bob, what he's going to do is he computes the grid cell distance as shown on this slide, and then remember, Bob cannot learn the actual distance because we use homomorphic encryption. And so in addition, what Bob does, he multiplies this value with a random value v. And so he returns this value, the ciphertext, to Alice. And now if Alice, again, but she cannot directly decrypt the ciphertext. The encryption scheme doesn't allow us to do this. However, she can try some possible values. In particular, she can try the value 0, right? Because if D is 0, the product of D and V is also going to be 0. So if the ciphertext is the encryption of the value 0, Alice will be able to figure out, right? So if Alice and Bob happen to be in the same cell, Alice will be able to learn this. On the other hand, if they are not in the same cell, D is going to be at least 1, and in addition we have a random value V which can be randomly large, meaning this product is going to be a random value, and it is very, very unlikely that Alice will be able to figure out which value was encrypted. Any questions so far? Right, so now if the value of D is 0, Alice will be able to figure it out.
Mm-hmm. Why multiply? Why not just use the random value? Non-zero random.
We need D, right? D is the actual distance. D in the grid cell.
What she's doing is checking to see if it's 0.
But we don't, right? For example, if we don't multiply it with the random value, and she's here in this cell, right? She should not be able to learn if Bob is in this cell, if the distance is 5, because we no longer consider this to be nearby. And so if we didn't perform this multiplication, Alice could just try all possible values starting with 1, 2, 3, 4, 5, 6, 7, and ultimately she might be able to figure out the distance. But with the help of this multiplication, this becomes very difficult. Right? Because again, V is randomly large. And only if D is 0, only then will the product be 0. Do you have another question?
My question was answered by the next one.
Okay.
If it's only for 0,
Yeah. Right. Again, right. This works only, what I've talked about so far, this works only for the middle cell where D equals 0. If D equals 1, we take a random value, and so the product is going to be, as I just said, it's going to be a random value 2. And it's very unlikely that Alice will be able to figure it out. And so how do we deal with the case where D is either 1 or 2? Well, what we do is we have Bob compute D minus 1. Right? So if D is 1, D minus 1 is going to be 0. And we end up with the same setup as just discussed. And similar for the case where D could be 2, so Bob just computes D minus 2, so if T is 2, D minus 2 becomes 0, and the product is going to be 0. And so what this means is Bob has to compute 3 ciphertexts, one for D, another one for D minus 1, and another one for D minus 2, and sends all 3 ciphertexts to Alice, and Alice tries to decrypt the 3 of them. And if she manages to decrypt one of them, she knows whether Bob is nearby. On the other hand, if she fails all the time, she won't learn any information. Any questions? Now, we actually implemented this scheme, and we used OpenSSL and a publicly available number theory library. We used 2048-bit cryptographic key and used a Pentium 4 to evaluate this scheme. And the numbers are shown on this slide. In particular, we show how long it takes for Alice and Bob to set up an SSL or TLS connection, and we also show how long it takes for Alice and Bob to do this computation. And so it's a little bit doing the encryption and decryption operations is a little bit more expensive than setting up a TLS connection, but it's not too bad. So basically what this means is if we have a device that is able to set up a TLS SSL connection, like for example many mobile phones are able to do these days, then these devices, they should also be able to perform this protocol. To demonstrate that this is really the case, we built 2 sample implementations of our protocol. One of them for the BlackBerry smartphone, which is shown on this slide. We don't have an implementation for the Android platform, but the software is publicly available, so if one of you is interested in using it on the Android, please download the software. And it's in Java, so it should be very straightforward to modify it. If you do so, please let me know, because I'm interested in learning about experience with our implementation on other platforms. We do have a second implementation. This is for the Pigeon instant messaging client, which some of you might have used yourself. And so, so you're basically instant messaging with a friend, and behind the scheme scenes, the scheme also exchanges location information with your friend, and if your friend happens to be nearby, you get alerted. So what you see in this slide is whenever somebody queries for your location, you get alerted. Right? We think this is a useful feature for privacy reasons. If somebody wants to figure out whether you're nearby, we better tell you in case there's a problem. And then on the next slide, we learned that a friend is actually nearby, and then based on this information, we can, for example, have ice cream together. And so again, if you want to play with this implementation, go to that address and you can download it. Any questions about this kind of application? Mm-hmm.
I still have a bit of a problem with people spoofing their own location and just randomly doing the spot check. Are you here? Are you here? Are you here?
Yeah.
Are you there?
So what malicious people could do is they could enter a wrong location into their protocol. And you might not have noticed, but so far I've been always talking about friends. So I wouldn't run this protocol for random people. But on the other, if you have friends and then they cheat, this might have an effect on the relationship, right? For example, your application tells you that Bob, your friend, is nearby, but then you fail to spot him, and so you can conclude that he probably cheated. So yeah, this could negatively affect your friendship, right? So, but I don't recommend running this application with random people because, as again, they could spoof their location. I think there was another.
Just curious, since the application is always sort of broadcasting these ciphertexts, how is the application on battery life?
We haven't evaluated battery life, and so the question was, how is the application on battery life? We haven't actually evaluated battery life, so we were more interested in the cryptographic performance. But this is definitely a topic of future work, and I'll come back to this towards the end of my talk. Some potential issues with this application. Yeah, good point.
Does the distance between the two friends have to be defined symmetric? Like if Alice wants to know if Bob is within 500 meters, but Bob wants to find out if Alice is within a kilometer, can they define that, or the protocol needs to consider about the same distance? So define the same distance as nearby.
It doesn't have to be the same distance. So the way we deal with it in our protocol is Alice chooses the distance she considers nearby and informs Bob of this distance. And if Bob doesn't feel comfortable with the distance, he just refuses to participate in a protocol.
Right.
Any other questions? Okay, again, if you want to play with this, please feel free and download it. So another application that I've been looking at in my research is are location-based services that return information that is relevant to your current location. So a key example here is Google Maps. So what I did here is I looked for coffee places that are close to the University of Waterloo. And so the problem with this kind of application is that in order for the application to work, we have to tell Google Maps, we have to tell Google where we are. And so we end up with the issues that I just outlined, like somebody learning our location. Some people react to this by saying, well, you don't have to reveal your identity to the service, you just use the service pseudonymously, like or even anonymously, right? So that the service is not going to learn your identity. There's a problem with this statement in that some locations, they are bound to a particular person. So even if you don't reveal your identity to the service, from your location, the service might still be able to figure out who you are, right? For example, your home, right? Your home is typically bound to you as your identity, right? So from learning the location, the service could infer your identity. Even if you issue a query from a place that is not bound to your identity, like, I don't know, a train station or a public square, right? Many people access a service in a continuous way, and so the service is going to see many queries over time, maybe all of them originating from the same IP address, and then once the query ends up at a place that is linked to the identity of the query issuer, the query issuer can be re-identified. And so therefore, using a service anonymously or using a pseudonym might not be sufficient. So what can we do instead? We could cloak our location. Right? So in particular, instead of revealing our fine-grained location to a service, we reveal a more coarse-grained version of this location to the service. For example, instead of revealing room 3526, Davis Center, University of Waterloo, which is my office, I just tell Google I'm somewhere at the University of Waterloo. Now, there's another problem here. Excuse me. In particular, just simply enlarging the area might not be sufficient. The problem is, if I enlarge the area and I happen to be the only person in the enlarged area, this is like the case probably if you had a more rural area, then, and if the service or if the enlarged area is under physical surveillance by the service provider could still re-identify you. So instead, what has been proposed is location cloaking based on K anonymity. You might have heard about K anonymity. This is a concept that was developed for databases. In particular, you have some sensitive records in a database, and you want to reveal these records in an anonymized form. And so the idea behind K anonymity is you release a record only if it can no longer be distinguished from K-1 records that also get released. And so for location cloaking, we slightly modify the rule, and the rule follows now. We cloak the location, so we make it bigger until it covers my location and also the locations of at least K-1 other people, right? And so there are K people, and which gives us an anonymity set of K people. They all have the same location.
That only works if location is the only signal that you have. So otherwise, inventing means that you need to K-anonymize across all signals, not just.
Very good observation. So simply K-anonymizing location information is not sufficient. We also have to K-anonymize other information. For example, what kind of information you're asking for. You have to K-anonymize, as you outlined, all the signals that are going to the service. And so that's perfectly true. And so I look at this as a first step, right? So the first thing we K-anonymize is the location. There's been other research that has looked into how to anonymize queries. Good point. So this K-anonymity approach. I'm not the first one to suggest this for location privacy. There has been lots of research that has looked into this approach, but there are some flaws with this existing research. Much of this research relies on centralized cloaking, right? So each device informs what I call location broker of its location, and then the location broker decides whether there's a sufficient number of people within a cloaked location, and if this is a case, we reveal the cloaked location to a location-based service. The problem with these solutions is everybody has to trust this location broker, right? The location broker knows all the time where everybody is, and as we saw a few minutes ago for the first application that I talked about, that's not what we want. Some more recent approach has suggested to get rid of the trusted location broker by introducing distributed cloaking. So now we have devices that talk to each other and that try to figure out whether there's a sufficient number of nearby devices. The problem with these approaches are that they assume that all the other users, that they are not malicious. And again, this might work if all the other users are your friends, but of course it doesn't scale like if you want to do this protocol with random people. And so what I'm presenting on the next slide is a Strawman approach. Instead of having one location broker, we have multiple location brokers. And if you think about it, this is what we have in real life, right? So there is not a single entity that knows, there's not a single cell phone provider that knows where everybody is at all the time. Instead, we have a limited number of cell phone providers, right? There is Rogers, who knows who some people are all the time. There is Bell, who knows where some other people know all the time. And so, right, so we don't have a single party only, we have these multiple parties that each of them knowing the location of a different set of people. And so what we can do is, if I want to know whether there's a sufficient number of people at a cloaked location, I just query each broker. They send me the number of people currently at this location. I sum up the numbers, and if there's sufficient number, I send the cloaked location to the location broker. Sorry, to the location-based service. This works. But there are so the big advantage of this solution is excuse me. It integrates really well with existing infrastructure. Again, think of the location broker as being a cell phone provider. But there are some drawbacks. it might be possible to track users based on data mining, right? So the easiest case is you learn that there is one user in a particular cell and there is nobody in the surrounding cells, and so now you might be able to track a person if this person leaves the cell. So this is a potential problem. Also, just from a design point of view, this is not necessarily a good idea. If there is a solution that allows us to solve a problem in a more privacy-friendly way, then we should choose this approach. This is what we call privacy by design, right? So try to build in privacy in the design solution early on. And another problem with the solution is, right, these location brokers, they are cell phone providers. And so now we expect them to reveal the number of customers within or close to a particular cell phone tower, for example, and do this to random people. But right, this could be sensitive information that a location broker is unwilling to share. So what I'm going to do next is I'm going to discuss a solution that is based on these approaches of having multiple location brokers. And so the user and the location brokers, they collaborate. There will also be a third party, a semi-trusted third party. And these parties then together determine whether the cloaked area has at least k people. And the nice feature of our solution is nobody, not even the user, not the location brokers, not the semi-trusted third party, none of these parties can learn the total number of people that are in the cloaked area. Before I outline our solution, I just want to point out the model, which makes it easier to understand the actual solution. So we have lots of users denoted by cell phones. We have a directory server which allows a user to query the available location broker. Each user is in a particular cell, and then she registers this cell as her location with her location broker, i.e. her cell phone provider. And then we also have some what we call secure comparison servers. These are required for our protocol. In an ideal solution, we wouldn't need these additional parties. We do have a solution that gets rid of these parties, but unfortunately, it turns out to be not very efficient. So the next slide outlines the protocol. I changed the setup slightly from the previous slide. So now we have the user in the middle of the slide, and we have two location brokers on the right side, and we have a secure comparison server on the left side. So the way the protocol works is the user asks each location broker about the number of people in her cloaked area. These location brokers return this information in encrypted form to the user. So the user is not going to learn these numbers. All the user can do is, again, using homomorphic encryption, she can sum up these numbers and send them to the secure comparison server. Well, actually, she's not going to send the sum. Instead, she's going to send the sum plus a random value r. In addition, she also sends her privacy preference k which has the random value r added to it. She also sends this value to the secure comparison server. The server decrypts the first value, the ciphertext, and then it simply compares the two values and informs the user of the result. Right? The result of this comparison basically says, is there a sufficient number in the cloaked area? Any questions about the basic protocol? It's important that everybody understands this because the rest of the slides depend on this protocol. So what I'm going to do next is I'm going to outline a few challenges. The first challenge is, if the secure comparison server, so the server on the left side, and the location broker, if they colluded, they could learn a user's privacy preference k. I'm not going to do the details, but it's possible to do this. And once they know this privacy preference k, the reverse process would allow the two of them to learn the total number of users in the cloaked area for future queries. And so that's what we want to avoid, right? Nobody should be able to learn the total number of users in a query. And so to fix this problem, if I go back to the previous slide, what we want to do is it should not be possible for the server to learn the value r plus k, right? It should not be necessary for the user to reveal r plus k to the server. Instead, the server should learn only the first value, so the r plus the sum of the individual numbers. And so basically the way we want to perform the comparison such that the user knows one of the values that are input the comparison, and the secure comparison server knows one of the values that are input to the comparison, but there is no party that knows both values that are input to the comparison. So this is one of the features that we need. Another problem is binary search, right? So in the protocol, if you go back to it, the user sends this value to the secure comparison server and asks it, is it at least k? And so right, the user, malicious user, could just modify the value of k, and using binary search, she could ultimately figure out how many users there are in the cloaked area. And so in order to avoid this, we have to make it impossible we have to make it impossible for a user to resend the same sum multiple times to the comparison server. The third challenge is a user could register his or her location with multiple location brokers, right? And so then each location broker counts this user as one person, but in fact it's always the same person, right? And so it should not be possible for the same person to register with multiple brokers. And another feature is collusion between a user and a secure comparison server. We also have to avoid this kind of collusion, because otherwise they could still learn the total number of users in a cell. So I'm not going to outline all the solutions to all the challenges in detail. I just give a high-level overview of how we solve them. We use cryptographic solutions for all challenges, but I also want to emphasize is that for some challenges you could potentially also solve them using non-cryptographic solutions. For example, if you look at the problem where we have duplicate registration, right? So what this means is a person, in order to register multiple times with multiple location brokers, a person basically needs multiple cell phones, right? And so she has to, I don't know, buy multiple cell phone plans, and so there can be economic reasons that make this kind of attack harder. So let's outline the solutions for the various challenges. So the first challenge, remember, this is the challenge where we want to perform the comparison executed by the secure comparison server and the user, such that neither of the two parties learns both input values, right? Each party should learn only one of the input values. And so we use an existing protocol, the GT-SCOT Protocol, or greater than strong conditional oblivious transfer protocol. I'm not going to give you the details of the protocol. I'm just giving you a high-level survey of how the protocol works. So we have the user's input, which is r plus k. Remember, r is a random value, k is her privacy preference. So she takes this value. In particular, the user takes each bit of this value and it encrypts each bit separately and sends it to the secure comparison server. The server takes its input value to the comparison, r plus the sum of the number of users, and encrypts each bit in the same way as the user, and then the server obliviously compares the two vectors, right? So the server does the comparison without learning which of the two vectors corresponds to the larger value. And again, I'm going to skip the details, but at a high level, the procedure is illustrated on this slide. So we have these two vectors, and the server starts comparing each bit, starting with the most significant one. Again, the server doesn't see the actual values. As soon as the server sees a value that is different, the server stops. Now again, the server is not able to see where actually the server stops. And depending on which value is 1 and which value is 0, the server assigns either the value 1 or -1 to this value, and all the other values are set to random values, and then the server shuffles this resulting vector. This prevents the user from learning the position of the bit where the first difference was detected. And finally, this result vector is sent to the user, which decrypts it, and then the user is able to retrieve either -1 or 1, and based on this value, the user can figure out which of the two vectors is larger, meaning the user will be able to learn whether the k-anonymity property is satisfied. Any questions about this? Again, you're not required to understand obviously the details of the protocol. How do we solve the second challenge? I'm not going to talk about the details. Basically, what we do is we use tickets. Right? So the user needs to be in the possession of a ticket, which is basically a digital certificate, and only if there is this ticket will will the secure comparison be able to execute the comparison. And in addition, the server caches received tickets, and if the server receives multiple tickets, the server will reuse a ticket that it has already seen. Duplicate registrations. Again, I've mentioned there can be ways such as buying multiple cell phones, which is costly, which might defend against this attack. A cryptographic defense against this attack is based on eCache, which you might have heard about. eCache is basically an electronic version of cash. So you have a bank, the customer withdraws money from a bank, spends the money with a merchant, and now an important problem with eCache is double spending. Obviously, it shouldn't be possible for a customer to double spend a coin. So when the merchant deposits the coin with the bank will be able to dispense double spending. And so in our solution, we use this eCache to avoid multiple replications. So the user initially gets 1 coin from the bank, and when the user registers with a location broker, she spends this coin, and the broker deposits the coin with the bank. And now if the user registers multiple times with maybe different brokers, this amounts to double spending, which can be detected by the bank. And so when the user deregisters, the broker withdraws a coin from the bank, spends it with the user deposits it with the bank, and then the user can get a fresh coin and use the fresh coin to register with the next location broker. And I'm not going to talk about the solution for the next challenge because I'm running out of time. Again, we have an evaluation of our protocol. This time the setup is slightly different. We run the server on a fast machine, and we run the user on an old laptop in order to simulate the capabilities of a modern smartphone. And so there are two protocols that we evaluated. So the first protocol is the communication between between the user and the location broker. And so here, remember, this is where the user queries the broker for the number of people registered with the broker. And so we have connection set up, which is 33 milliseconds, and we have the encryption operation. And as it turns out, the encryption operation is actually cheaper than doing the connection setup. The second operation is the comparison operation between the user and our secure comparison server. Remember, this is a bitwise operation, so each bit is compared individually, and so that's why we have on the x-axis the bit length, and on the y-axis we have the actual delay. And so we give the delay for various components of the protocol, like the server and the user. The curve we are most interested in is the blue one. This is the curve for the user. And as you can see on this slide, the delay varies between 200 milliseconds for a bit length of 4 and a delay of about 600 milliseconds for a bit length of 16. In practice, we think that bit lengths of 8 and 12, between 8 and 12 bits are sufficient, and so the delay is going to be on the order of 300 to 500 milliseconds, which of course is noticeable, but we think that this is also tolerable in practice. Okay, let me conclude my talk. I hope I've made it clear that together with the upcoming of all these mobile applications that take users' location into account, another important issue that is arising is location privacy. So we have to clearly control who should be able to get access to a person's location. And so there are multiple ways to deal with this problem. There's been lots and lots of research on this topic. I'm not claiming that this is a complete survey. I just presented two particular algorithms that turned out to be useful in practice. The first one was based on cryptographic techniques, like, well, actually both of them were based on cryptographic techniques like homomorphic encryption, and another popular technique is based on k-anonymity. And as our implementation and evaluation has shown, it is actually possible to deploy these algorithms on real mobile devices, right? It's not just a dream that we're having. Some future work. The first item has already been pointed out in a question, right? As I showed with the slide, the BlackBerry, it is possible to run the protocol on a BlackBerry because the performance is similar to setting up a TLS connection. Problems arise when you have, for example, lots of friends, right? Some people, if you look at their Facebook accounts, they have dozens or maybe even hundreds of friends. And so, right, if your cell phone has to run this protocol every, I don't know, 5-10 minutes with each friend, this is going to take up lots of resources. So resources meaning both computational resources, but also battery resources, or communication resources, which can be a problem, like in places like Canada, where communication can be expensive. And so for people that have lots of friends, our protocol might be too expensive. And so instead, what we would like to have is a protocol where we can offload computation to a third-party server. In particular, this third-party server should do the computation, but it shouldn't learn much information. Right? I'm not saying it shouldn't learn any information, because this presents an interesting problem in terms of incentives. Right? So, for example, if you think about Google running this third-party server, so Google is doing computations on behalf of lots of people, but it's not learning any useful information while doing this computation. So obviously Google wouldn't have much of an incentive to do this, right? So the question arises, what kind of information can we reveal to Google, to this third party, while doing this computation, such that the third party still gains a profit from this computation? Like, I don't know what the solution is. Maybe we reveal a person's close-grained location to the third party, such that the third party could, for example, serve location-based ads to the user. Another item of future work is for the second protocol that I talked about. What we would like is, what we really would like to have is a solution that doesn't require these additional third parties, the secure comparison server. We have a solution, as I mentioned, but it doesn't turn out to be efficient. So this is still open. And finally, which is the next item, which is probably the biggest items, right? I've just talked about two applications in this talk, but there are, of course, lots and lots of other applications that are out there. I don't know, location-based games or location-based matchmaking, right? So you tell your cell phone about your current interest, and if somebody else happens to be nearby, the cell phone with the same interest happens to be nearby, your cell phone alerts you. But of course, there are obvious privacy problems with these kinds of applications. So the question arises, how can we build all these applications with more privacy in mind? Before I conclude my talk, briefly let me give you some credits. Most of the work in this talk was done by Ji Song. He was my master student, and to some of the work, my colleague Ian Goldberg, he also contributed a part. And finally, I also would like to acknowledge NSERC. Okay, thank you for your attention. Are there any questions?
All right, if there are no questions, thank you.
Thank you.